Okay, physical science time. Today we are talking about the atom. So please write down the atom. Today's objective, as you can read, is diagram the structure and function of subatomic particles. Let's talk a little bit more about that. Diagram the structure and function of subatomic particles. Diagram, what's that word mean? Shut that door, shut both those doors, please, Joe. What's the word diagram mean? Yeah, like to, what would the verb you would probably use be here in this class? What are you going to do? If you're diagramming, what are you going to be doing physically with your pencil? Drawing, probably. So diagram the structure, what's that mean? Yeah, what it's made of. And function, what's that mean? What it does. Yeah, what it does of an atom. I'm actually kind of actively looking for a better verb than, or sorry, better noun than function there. Because function to me kind of implies that like it's up to something, like oh, I got to go to my job today. But atomic, at least as far as we currently understand, subatomic particles aren't thinking. They're not consciously deciding to do this and this and this. They're just, it's what they do. So basically we're talking about what they are, the structure, and what they do, the function of subatomic, I'm sorry, it says an atom. I wrote that down wrong because the objective actually is subatomic particles, isn't it? Subatomic particles. You know what a particle is, but what's subatomic mean? Yeah, the components of an atom. So let's talk about what an atom is, and then we'll talk about the components, the subatomic particles. What is an atom? Okay, the smallest what? The smallest thing in the universe? Not quite. Okay. You had it in a definition in your vocab that is good. The smallest of element, the smallest particle of an element, because as we'll find out, so the atoms are made of subatomic particles, but all the subatomic particles are the same. Like in your lab, you had orange ball, blue ball, green ball. I don't know what the actual colors were, but you had 3 different colored balls to represent the subatomic particles, but those were all the same as each other, right? There's no difference between a proton of magnesium and a proton of silver. It's just how many of them there are. That's what determines what element it is. So an atom is the smallest particle of an element. It comes from the word A. Do you know what the prefix A means when we talk about Greek words? This is the Greek letter alpha. Do you know what that is? Like in asexual is what? You probably remember that from 7th grade science. Asexual is something as opposed to sexual reproduction. Asexual reproduction, yeah, is not. The prefix A in all of the Proto-Indo-European languages means without. So A, without, or can't, or won't. You know, the negation of. So A is the negation of the tomos, and this is in Greek, the tomos. Tomos means, this one's, you probably don't know this, but if you've ever heard of like a CT scan, is computerized tomography. The way that what it does is virtually slice up your body so you can see your body in slices. And so tomos means to cut. So the atomos is that which cannot be cut. And that's the name. So does that mean that atoms can't be broken up? No, we just talked about subatomic particles. But the name comes from that which cannot be cut. Can't be cut. It's the thing, the philosophical idea of the atom comes from a man named Democritus, and I don't think for your test you need to write this down, but in chemistry you will. A Greek philosopher named Democritus was kind of, as all the Greek philosophers were, was drunkenly sitting around. He'd had 18 gallons of wine that day, and he was like looking at the stars, and he was like, what if there was something that couldn't be cut? And that was it. Like, what if I'd cut this cheese, and I got to a point where the cheese was so small I couldn't cut it anymore. Let's call that can't be cut, the atom. His was just a thought experiment, but then later, when the atom, what we now understand as the atom, was in a essence discovered, they named it after his thought. So it's called the atom. So that thing which cannot be cut. An atom, as you said, has all the properties of that element. So it's made of subatomic particles. Subatomic particles. What are they? Okay, let's actually, I'm going to make this into a little chart. Name, symbol, location, mass, I need another column, and charge. Those are the things we're going to talk about. There are more, especially when we get into quantum mechanics, but these are the main ones that we're going to talk about at the freshman and high school level. So name one. Let's do them in different colors. What color do you use for electrons in your lab? These are not, there's no set color they have to be. Pink. Okay, I do have pink. So the name is electron. The symbol is the lowercase letter E, the lowercase Latin letter E with a little negative sign in the corner. Location, where is that little guy? Yeah, not in the nucleus, right? We're going to put electron cloud. And we'll talk more about that later. What's his mass? Yeah, effectively 0. I'm going to put about 0. When we're in chemistry, I think it's 1/1840th of the mass of the other two. So 1/1840th. Very small. It would take over 900 of them to even round up to the mass of one proton or neutron. So we basically say it's 0. In all the things that we're counting the mass of electron in chemistry, you don't need to count it. It's a rounding error. Charge. What's the charge of an electron? -1. It would be nice if someone besides Aiden Streety would answer some of these things too. What's another one? You have to write this down, Corbin. Proton. Thanks, not Aiden. It'd be nice if someone besides Aiden would write these down. I didn't mean that. I do mean that, but it would also be nice if someone besides Aiden would say them out loud. Proton. Okay, Aiden, why don't you, I appreciate your input and I really value your discussion, but why don't you pipe down for a little while because someone else needs to show this. The symbol is just the letter P. Where's that little guy? Okay, and where is that little guy? In the nucleus. In the nucleus of the cell? No, nucleus is a Latin word that kind of means like the philosophical center of, even if it's not in the actual center. It's the main point of it, the central component of it is what a nucleus is. And so when we talk about nuclei of cells, that's a different thing, although it is made of nuclei of atoms and electrons too. But the nucleus of an atom is kind of the central, the locus of its mass, the place where its mass is. Speaking of mass, what is the mass of a proton? Not Streety. It's a number. It's not 0. It's a non-zero number. It is an integer, or it's approximately an integer. It's 1. Its mass is 1. AMU. Atomic mass unit. Atomic mass unit. Well, that's kind of a lazy title, but that's the unit we use for the mass of subatomic particles. And its charge? +1. Very good. Thank you. What's the last of the 3 main subatomic particles? Neutron. The symbol is the lowercase letter n, which I drew a terrible example of. Where do you think that little fellow is? Also in the nucleus. What do you think its mass is? Also 1 AMU. What do you think its charge is?
-1. No.
Like the electron? It's none. Yeah, it's none. It's neutral. That's why we call it a neutron. As kind of a matter of interest, which one of these do you think was discovered last? The neutron, yeah, because it was hard to detect because it has no charge. Electrons were discovered when we noticed that atoms had a component that was negatively charged, using what's called the cathode ray experiment, which we'll talk about in chemistry. Protons were discovered, not really so much discovered, but inferred, because if there's a part of the atom that is negatively charged, the rest of it must be positively charged, otherwise it would have a charge, and it doesn't. And so the neutrons were the last ones discovered because they have no charge, and so they were harder to detect. These are one way to think about them, my favorite way to think about them, it's easy to think of them as like very miniature versions of clay balls, and they're just like basically matter but smaller. But that's not quite true, and even the way I'm going to tell you is not quite true. And we're always in science actively trying to find the truth of how these things work. But one of the coolest ways I think to think about them is in the universe. The universe is basically made. We've said before, the universe is made of matter and energy. Well, these are what make up matter. And really all the universe is a blob of 4 force fields. There may be more, but we think 4 force fields. And those are the 4 fundamental forces. We've talked about this before, but please write this down. The 4 fundamental forces. The 4 fundamental, what's the word fundamental mean? Yeah, forces of the universe. The word that was posited was basic. The 4 most, the 4 most, most basic is pretty good. The 4 inseparable forces, the 4 forces that make up everything, and they are in order of strongest to weakest. Do you remember them? What's the strongest of the 4 fundamental forces? Strong nuclear. I wish that I had done these in different colors. 2, also remember I was going to do these in different colors too. Check it out, but I didn't. Strong nuclear, what's the next strongest, you remember? We talked about this one a couple of months ago. No. Yes, electromagnetism. Electromagnetism. Weak nuclear. And then finally, gravity. Red. Is this already picture in picture? Like, is it just the board and then me in the corner, or is it just all one thing? The big one is the board, and then in the corner is me and the board together, like a zoomed out version. Okay, so now if I do this, did it change? And now it's mostly the board, so you can see the board a little better. Okay, good. Okay, so I think a cool way to think about these is that the universe is like unto a bubble where it's only these 4 things. I mean, literally only these things permeating all of empty space. These are all 3-dimensional fields. And excitations in that field, just like a wave is an excitation in a water field, like there's a surface of water, and a wave is an excitation in that. Are you with me so far? Yeah, because that kind of makes sense. That this is an analogy. But the strong nuclear force is excited in those nuclear particles. So the strong nuclear force is excited in the proton. The proton is an excitation in the strong nuclear field, and a neutron is an excitation in the strong nuclear field. Which ones of these do you think are excitations in the electromagnetic field? Electron, because it has an electric charge. And what else? Nope, not neutron, because neutrons are neutral. Proton. So protons are also excitations in the other direction than an electron, because they have a positive charge, but the same amount. What about weak nuclear? Which ones do you think are excitations of the weak nuclear force field that permeates the whole universe? Not electron, it's weak nuclear. Proton and neutron. And which ones do you think are excitations in the gravitational field? This is really exciting because the fact that a gravitational field permeates the whole universe was kind of confirmed by an experiment that happened in like 2020, a LiDAR experiment with black holes. It proved the existence, well, I shouldn't say proved, provided very strong evidence for the existence of a gravitational field that has waves in it. Which ones do you think excite the gravitational field, or excitations in the gravitational field? Proton, because it has what? What would an excitation in the gravitational field be like? Yes, only attractive, but because it has, what thing attracts all things with gravity? The fact that things have any, yes, mass means they attract each other with gravity. And so neutrons do too. So these particles are kind of like, a proton is a place in the universe. You can think of it as a place, even though place has almost no meaning on that scale. A proton is a place in the universe where all 4 of the fundamental force fields are excited. A neutron is a place where the strong nuclear weak nuclear and gravitational fields are excited. An electron is a place where only the electromagnetic force field is excited. I think that's a cool way to think about it, because this is inextricably linked. These are inextricably linked, meaning they can't be unlinked with these. These are manifestations. These are physical things that happen because of these. And these, you'll recognize, are kinds of energy or forces. And these are what we call matter. They're the same thing, baby. They're the same thing, baby girl. Matter and energy are one thing. There are really only two things in the universe. This matter energy and space-time, and that's it. And everything is just different combinations of those. What are we talking about, though? There is an important thing that we have to do with this. The math that we have to do with these is that for a given atom, specifically a given isotope, what's an isotope? Yeah. Type of atom with a specific number of neutrons. Remember, a type of atom, what's another shorthand for a type of atom? These are the different types of atoms, so we might call that a element. So if I gave you an isotope, we should be able to tell how many protons, neutrons, and electrons it has. That's our math. That's our worksheet. And we can diagram these in different ways. So one of the things you do on your worksheet is show, let's do the math thing here and the diagram here, which will also satisfy our objective for these. And I really wish I had done these in different colors, but I chose not to. Actually, let's redo them in this. What color did you do protons on your? Proton? No, let's pretend they weren't, because I don't want to write in yellow. No one will see it. Were they? What color were neutrons? Okay, I was going to say, because that wouldn't be good either, would it? So we don't want to have two of the same. I could have just, now that I think about it, I could have just erased the word. Neutron, symbol in location, nucleus, mass 1, AMU, charge 0. Okay, and then let's pretend you said protons were orange. Nice, protons are orange. That's sick. Go Rams. Protons, symbol P, location, nucleus, mass 1 AMU, charge +1. There we go. Okay. So let's do a simple one to start with. Let's say helium-4. That's a nice easy one. So we have an element of helium. Let's write it this way first. 4, which we also sometimes indicate with its symbol with the mass number up in the corner. Now check it out. This number is the mass. Write this down, please. The mass number. The mass number. It's not. Look at helium. See how it says 4.00260? Do you see where it says 4.00260? That's the average atomic mass, and that's a different thing. That is useful, but it's not the mass number. The mass number must be given to you when the isotope is given to you. So helium-4 is a specific isotope of helium. That is a specific helium atom with a specific number of neutrons. So this particular helium atom that we're discussing has a mass number of 4. Okay? So what's its total mass, do you think? For what? AMU. Okay, so we're going to both diagram and do the math for this. There are two ways, again, let me reiterate, there are two ways to write this. The word helium-4. What's the 4? Mass number. And also its symbol with the little number 4 up in the top left corner. What's its mass number? 4. Okay, so the two ways to write, the two ways to figure this out are, first we write down its number of protons. We just write P. In, what do you think N stands for? Neutrons. And E minus. What do you think E minus stands for? Probably tornadoes, yeah. Electrons, yep. Okay, how many protons does it have? Well, for that, we go to the periodic table. Helium has 2 protons. Every atom of helium in the universe has 2 protons. Every atom in the universe with 2 protons is helium. So how many protons must the helium have? 2. So we write down 2. Well, how do we know it has 2? Because it's helium. How many neutrons does it have? Well, in this case, it has 2. Its mass is 4, and the only 2 that have mass, that excite the gravity field, or that have mass, are protons and neutrons. So here's the very, very, very basic formula for this chapter. Protons plus neutrons equals mass number. That's it. Protons plus neutrons equals mass number. That's it. So if I'm given the mass number, how would I find how many protons? Or sorry, how would I find how many neutrons? Just subtract the protons. Are these always the same? No. In this case, they're the same, but they're not always the same. Speaking of that, though, the electrons and protons are the same. These two, unless there's a charge, I'm going to put in neutral atoms, they are equal. They are the same. Because that's what neutral means. The same amount of positive as negative. The negative and positives cancel out. So in a neutral atom, like this helium-4, they're the same. Now let's diagram that. Well, where should I put my two protons? I have proton color here. Where should I put them? In the nucleus. 1, 2. Where should I put my green neutrons? In the nucleus. And I should make them roughly the same size. And where should I put my pink electron? Somewhere else, right? Maybe like that. The classic way to draw it, in what we call the Bohr model of the atom, named after Niels Bohr, is in an orbit, like the planets orbit the sun. We know that's not how they are. Niels Bohr's hypothesis about that is based on the fact that they have energy levels, which we'll talk more about in chemistry, but they have energy levels. They have different amounts of energy they can have. He represented as different orbits. We even still call them orbitals. But in reality, it's way cooler than that. The electrons exist in what's called the electron cloud, which we talked about before, which is an area around the nucleus where electrons could exist. And what they do is, since their excitation's in a wave field, they exist here, and then they basically teleport. Now they're over here. And they just are at random places around the nucleus, which we call that area where they could be or are likely to be the electron cloud. And then they excite different areas in that field around the nucleus. So we find how many protons, neutrons, and electrons an isotope has by using its mass number, in this case 4, and its atomic number, which for a given element is always the same. Do you have questions about that? So let's look at this little worksheet real quick. Here's the worksheet. Is that showing up? Okay. Let's look at number 2 on the worksheet. Let's all look at number 2 on the worksheet. Name blank. Oh no! The name is blank. We don't even know what it is. Atomic number 8. Do you see why it's okay that the name is blank now? It's oxygen. How did he know? He just guessed and he's right because your boy told him? No. How did he know it was oxygen? It has no name. Its atomic number is 8. Remember I said this of helium, but it's true for oxygen too. Every atom in the universe with an atomic number of 8, with 8 protons, is oxygen. So you can go ahead and write oxygen in that little box. Okay, the next blank is number of protons. Well, if its atomic number is 8, what must its number of protons be? 8. Why don't you go ahead and draw a little arrow between the heading atomic number and the heading number of protons? Those are the same. All the way down. Every single one of those is going to be the same. Atomic number and number of protons must be the same. Now it says number of neutrons, 8 also. Do those have to be the same? No, they don't have to be, but in this case they are. How am I going to find the mass number? I add those together. So if I have 8 protons, each of which has a mass of 1 AMU, and I have 8 neutrons, each of which has a mass of 1 AMU, what is my total mass in AMUs? 16. So write 16 in the mass number. And this isn't part of it, but how would you write the isotope name for that? You'd write oxygen-16. Could you write it in this notation? Yep, capital O with a 16 where? In the top left corner, right?